Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Thursday, November 2nd, 2023. It's my great pleasure to be here with Professor Kevan Shokat. Kevan, wonderful to be with you. Thanks so much for joining me today.
Thank you, David. This is great. Been looking forward to it.
Kevan, to start, would you please tell me your titles and institutional affiliations?
Yes, I am Professor of Cellular and Molecular Pharmacology at University of California, San Francisco. I'm also a Howard Hughes investigator and also a Professor of Chemistry at UC Berkeley.
Now, the duality of the appointments between Berkeley and UC San Francisco, does that just give you wider latitude in terms of research tools and collaborations? What's the interest in there for you?
Yeah, it was mostly to expand the chemical biology access of students across the two universities. So a number of years ago, some students at Berkeley, were interested in chemical biology, and there were a few labs, but actually the departure of Peter Schultz made it a little bit sort of less attractive. And so when I was recruited to UCSF, I received an appointment at Berkeley to sort of expand that ability of students. So it's kind of to help student recruitment and give them more options in one sub area of chemistry.
Kevan, being a Howard Hughes investigator, is that more of an honorific, or does that really allow you to do things that wouldn't be possible without that?
Yeah, the latter. It's basically about $1.5 million grant support a year for 7 years, and then it's renewed. So it's a kind of a grant that is given to a person and their lab, not to a project. So the money is very sort of flexible in terms of projects, and so that gives me a huge leeway to do things.
Kevan, being in the Bay Area, working at the interface of chemistry and biology, how translational is your overall research agenda now relative to what it might have been a decade or two ago?
Yeah, no, 2 decades ago, it was really just very barely translational. But something happened about 24 years ago, which was the approval of Gleevec, the drug that treats CML, a kinase inhibitor. And that was kind of like the first targeted therapy. And we were working on protein kinases. So, seeing a drug approved in a family of proteins that we were working on all of a sudden kind of had me raise up my head to look around. And then since that time, it's just gotten more and more translational.
Now, does that mean that you have direct interface with biotechnology companies? Are you ever in the hospital? Are you involved at all with the Chan Zuckerberg initiative? Things like that.
Yeah, no, I don't do anything in the hospital, and I don't have any affiliation with the Chan Zuckerberg initiative. As it turns out, Howard Hughes investigators are not allowed to work with the Chan Zuckerberg. There's some disagreement on what nonprofit research means, I guess. I don't know exactly what it is, but I do work a lot with biotechs. Yeah, we started a number of them and licensed a number of compounds to pharma companies, and sit on a number of boards and things. So that sort of helps our molecules get farther down towards the clinic and approval, and it also sort of helps me understand like what are the challenges they're facing, and are there things in basic questions that we could investigate that would help sort of solve problems that pharma companies are facing, and then 10 years later then have that product and sell it to them. Yeah.
Just as a snapshot in time, November 2023, what are you working on right now, and more broadly, what's interesting to you in the field?
I think the two things that we're working hard on is basically there's targeted therapies, which are the kinase inhibitors, and now these KRAS inhibitors that we helped make. And then we know targeted therapies in cancer patients, they can have a great effect, shrink the tumor, but often the tumor comes back. And on the other side of immune therapy, we know that can be a cure, but only in a subset of patients. So what we're trying to do is bring those two things together and engage targeted therapies in a way that educates the immune system to also attack the tumor. So that's what we're working on. We work on new targeted therapies. If there's no drug, we work on that. But then the linking of the two things is what we're really we think that could be a real kind of breakthrough combination therapy.
Tell me about the graduate students and the postdocs that are attracted to work in your lab. Do any of them have an MD, or do any of them have aspirations to really work in a clinical atmosphere given the research focus that you have?
Yeah, no, starting with one student, Beth Apsel, about 10 years, no, more than 10 years ago. She was the first MSTP, medical science training program student in the lab. And since then, I've probably had about 8 or 10. And so there's usually one, two, or three at a time in the lab. And I think they really like the idea that the things they work on can lead to a drug. And there's a real patient population in mind when they're working on that. And one of them that worked in the lab was John Ostrom, who is back here now at UCSF as a lung cancer oncologist. And he worked with a postdoc, Wolf Peters, and discovered the first KRAS drug. So that's a pretty amazing thing for a student that's going to become an MD PhD student to have participated in. So that's he really it's been fantastic to see that. Yeah.
Kevan, the breakthrough that you referenced earlier from 24 years ago, was that more of a conceptual eureka moment? Were there breakthrough technologies that made this happen? Was it really just about grinding out in the lab? What accounted for this?
Yeah, it's fascinating. It really, I think, was the brainchild of Brian Drucker, who's now up at Oregon Health Sciences. And he really just recognized that this BCR-ABL oncogene transforms cells. It's in almost all of his patients that have that disease. And he knew that a chemist at Ciba-Geigy, Nick Leiden, had made a kinase inhibitor of that. And he just said, we should try this. But Novartis was very resistant because there were only about 10,000 patients. And so he had to, kind of just keep explaining the logic. And then finally, once the trial was there, I mean, people from all over the world were just a magnet to Portland to get on his trial. And it made Novartis billions despite the small number of, so it overcame so many biases, small patient population. Hey, it's a breakthrough, transforms their life, and also they stay on the drug. I mean, it's amazing how people didn't see all it before, but he really brought that.
Kevin, I wonder if you can reflect on how the life sciences, biological research, has really become big data over the past 20 or 30 years, and how that's affected your lab, how that's affected your approach to computation, or even more recently, AI and machine learning.
I'd say that it hasn't yet made a difference in our lab. I mean, partly I'll give you an example. You might think AI is going to tell us about new drug targets and we can mine so much data. But actually, the target we worked on, KRAS, that was discovered in 1964, discovered to be a human oncogene, the first one in 83. And then subsequent to that, 30% of all cancers have that same mutation. So it's like we've known about that, but nobody could make a drug for it. So we didn't need AI to tell us about KRAS, And then whenever we've tried to use computation, it has not helped us with that project because the protein's flexible and nobody saw the pocket until we had a drug that made the pocket. So it's the kind of we kind of tend to work on problems that at least right now haven't been a breakthrough there. I mean, but it's changing very rapidly. On Monday, AlphaFold people said they have a computational approach for small molecules now. That's what we've been waiting for. So I might have a different answer next week.
Kevan, staying on the technology theme, what about instrumentation? Have there been breakthrough advances in microscopy or lab techniques that have really pushed discovery ahead in the course of your career?
I would say for us, the a really good thing is just mass spec has been much more user friendly, more sensitive. So we've got our own mass specs now for proteomics, for small molecules. That's helped us with just synthetic chemistry and proteomics. Um, we don't use microscopy a ton. I mean, I'd say the biggest thing is NGS, sequencing. It just can't be, overestimated. It's so powerful.
Kevin, let's get to the main topic at hand now. I'm learning about the development of chemical biology as a discrete discipline and the institutional role that Caltech played in it. So let's just start with terminology. What does chemical biology mean to you? And has that term changed since you first encountered it, maybe as a graduate student?
Yeah. I think right now chemical biology is to me means using chemistry to study biology. So I think the way it started was with the term would have been bioorganic chemistry, which grew out of several subdisciplines, but natural products and sort of trying to emulate biology with small molecules, Ron Breslow's, host guest chemistry. And but I think now chemical biology is kind of like now using, you know, as much as I like to say, I mean, as much as chemists like to say chemistry is the central science, I do feel like biology somehow really became the, the orb that we're trying to sort of understand. And I think chemists realize how powerful chemistry is to study that. And so that's what the sort of chemical biology is. And then I sort of think of chemical biology as it is a path to a drug, but it doesn't always have to be. So, and then I think the other term people wonder about is what is pharmacology, because that's using chemistry to perturb biology. And what I like to say is that, when chemical biology works, it becomes pharmacology because, hey, everything all works. You can put it in an animal, you can put it in anybody, and it will, so that's kind of the transition point, like borders of things.
The metaphor of biology as the bigger orb. Is that to say that biology is just so interesting, that it's so vast, that it's sort of, it's just too interesting for chemists not to pay attention to? Is that the broad story here?
I like that, but I also like that it is in a way it's bounded. So, chemistry, we know the chemical diversity is more diverse than atoms in the universe. We can make more molecules than we have atoms in the universe. So you can just keep making molecules. But if you're really trying to study biology, it really forces you into a box, and you have to make your chemistry work there. And to me, that is a lot more. It creates a different kind of creativity. It really forces you to do it. I mean, I think in Peter Durbin's work, forcing himself to stay in the minor groove of duplex DNA and how to recognize that, year after year until he could do it. That's exactly what I mean. It's like, no, I'm not going to bind to some polymer. I'm going to bind to this polymer. So, yeah.
I'll ask more of a sociology of science question, and that is, who is in the club of chemical biology? In other words, 30 years ago, when it would have been almost exclusively chemists who were interested in solving biological problems, is that more or less true today? Or do we see biologists now sort of reversing that, and they're interested in chemistry and they're calling themselves chemical biologists also?
Yeah, that's a good point. I think there have been biologists that, did their PhD in biology and then went into chemistry or chemical biology labs and then came out as chemical biologists. The person that I think of is Craig Crews, who did his PhD with Ray Erickson, signaling ERK pathway, and then did his postdoc with Stuart Schreiber and then now he does, proteolysis targeted chimeras. So, a real chemical biologist. So there are people like that. It's definitely fewer. I still think a lot of people come from a synthetic background, go into chemical biology labs, and then they become chemical biologists.
Now, because there's always a story behind the administrative decisions of which faculty sit in which departments, where is chemical biology at both UCSF and Berkeley? Where would the chemical biologists sit in the bigger schools?
The bigger schools always in chemistry. I honestly still don't think biology departments or molecular biology departments, they do not. I will say they do not like chemical biology. Because I think it's just a different, biologists, they're interested in the problem. They will use whatever tool they have. Chemical biologists, they have the tool of chemistry, so they've got to look for problems that match. So, yeah, I think when I looked for my faculty positions, no bites from molecular biology or anything. That was a long time ago, but I still think it's true. Yeah.
We'll go back and establish some personal history, but before that, I wonder if you've ever thought about the academic and intellectual lineage that connects you to Peter Dervin, of course, through Pete Schultz. What does that look like in your mind?
I mean, I definitely, it's just a definite direct track. I sort of, I think my career was really changed when I met Pete in my interview for graduate school at Berkeley. Went into the office, heard about his 3 projects, left the office. That's the only thing I wanted to do, So, and then as I got to know Pete, and then got to know Peter Dervin and what Pete did in Peter Dervin's lab, and then see Peter Dervin's, career and discoveries keep impacting. I could kind of see the strands, that connected them. And and Peter Dervin was very supportive of me early in my career, even though I hadn't trained with him. He provided letters and was really, really, really helpful. So it was nice to be in that sort of arena that a student of Schultz's was definitely supported by by Peter Dervin.
Let's establish some context before you get to Berkeley. So as an undergraduate at Reed, were you already thinking about chemistry and biology and connecting the disciplines, or that really only became real for you once you met Pete Schultz?
I think it was more enzymology at Reed. So it was like traditional biochemistry that I was doing. And then, then when I heard the projects that Pete was working on, it just dawned on me, wow, you can do chemistry and manipulate or study biology. I was just like, wow, that's not anything I conceived of as an undergraduate. But it just, it immediately clicked. So, yeah.
Coming from a small teaching focused 4-year school to an enormous research university, what was that transition like for you? Did you encounter professors as an undergraduate who were engaged in original research?
Yeah, they were. At Reed, you do a independent thesis, so you actually spend a whole year doing your own research project. And mine was with a professor named Ron McClard, who was very prolific, had his own grants, and so it was a very intensive research project. And I published 3 papers there, and each time month went by, I got more and more excited about research. So got definitely a lot of exposure there.
Beyond Berkeley, where else were you considering for grad school?
MIT. Yeah, I was thinking of MIT to either work with Chris Walsh or Bruce Kemp, and our Dan Kemp, and that it just. But once I met Pete, it just seemed to really. And I was from the Bay Area, so that was also another. Yeah. Also visiting MIT in February or March, that's
Never
a
helps.
sure. Somebody from California.
You mentioned Pete's 3 projects that were so compelling to you. What were they? What was he working on at that point?
Sequence-specific DNA cleavage by taking a non-specific DNase and attaching an oligo to it to sort of bind and then cleave. And that was Dave Corey's project. And the other one was a unnatural amino acid mutagenesis, 21st amino acid, stop codon, suppressor tRNA. And then the third one was the one I worked on, which was catalytic antibodies, getting the immune system to make enzymes. And I mean, each year that goes by, I think about those three projects. They're mind-blowing. The first one is basically a chemist's version of CRISPR. You know, it's like the thing.
I wonder if you can narrate. I mean, I understand, but I wonder if you could narrate the significance of that comparison.
I mean, yeah. So, Pete realized from working with Peter Dervin that, recognizing DNA sequence specifically and cleaving it and doing it at resolution that would allow you to be single site specific in a whole genome was like, that's the goal. We have to get there. And he knew about sequence specific enzyme, sequence non-specific nucleases that could cleave anywhere, but they were just misdirected. So he then attached a cysteine, a new cysteine, and then an oligonucleotide with a thiol. They made a disulfide. So now you would direct your DNase non-specific to where it would hybridize. The thing worked. But the problem was it's the whole protein with the DNA attachment. Now what CRISPR is basically a nuclease that has a guide RNA that binds non-covalently to the non-specific, and then it cleaves. So if Pete had engineered it to bind an oligo non-covalently and redirect, that would have been CRISPR. It's amazing to me. So yeah, I chastised Doug Clark, the Berkeley dean, when he introduced Pete a number of years ago, because he introduced Pete about 21st amino acid and catalytic antibodies. Like, Pete, I was like, Doug, you didn't mention the CRISPR, the early CRISPR.
Kevan, you're slotting into the catalytic antibodies. Was that your choice? Was Pete Style as a mentor? He assigned you to that group? How did that work out?
Yeah, I think he just, he just had so many ideas. And Andrea Cochran and I were the two graduate students that joined that year. And he just had, 6 catalytic antibody projects. Andrea got 3, I got 3. And then by the end of it, I had like 10 projects. Yeah, so I think it was, yeah, it's, I think he had a very good sense of which projects were right for people to join, where did we need more person power. He also kept a very good eye on the progress, so he could tell, are we getting this closer, or are we running into walls? And so after about 4 years in the lab, he was like, Kevan, the projects we started on are just really hard. They're not quite getting there. We have a postdoc who's leaving, and he didn't finish a couple projects. Take those over. And those turned out to be my first really big projects. So I was really grateful that he, always had a sense of where to move the people and get things done. And it taught me a lot how to run my lab about that.
What were the big research questions that drove your thesis work? What were you after?
We were after, the biggest one was basically a designer protease that could cut amide bonds anywhere we wanted. And the challenge was that antibodies really have never been able to do that. They don't have the flexibility, the catalytic horsepower, if you will, to do that. And every time we tried to isolate one, we had the problem that it could have been contaminated with a protease, natural one. And so I really kind of advocated for trying to cleave a non-natural sequence. I think a lot of us in the lab did, so that there would be no chance that we would be fooled by a contaminant. And so by the time we kind of worked through that, we just were 0, 0, 0, 0, 0. But at least it taught me, like, okay, that's a good control. Like, make sure you're not going to get fooled and things. So So it was I loved the time in the lab and all the people in the lab, and it was a very, very special, you know, feeling, and just fully engaged. It was great.
Kevin, I wonder either through osmosis or explicitly from Pete, did you get a sense of the legend of the Dervin lab, what was going on at Caltech, or that came later for you?
I think that came later. Yeah, I guess Pete was really just so it was just so all consuming starting his lab, because that was in the I was in the third group of students. So it was like when I joined the lab there were like 9 people. When I left there were 40 people. So it was a pretty
What explains that explosive growth from 9 to 40?
it's the number of ideas and the ambition, I would say, and the number of good ideas to pursue. There were, cleave DNA, cleave RNA, make a protease, make a glycosidase, make a charismatic mutase, there was all the 21st amino acid stuff. It just every project, just what I loved about it is it had an amazing goal, but then he broke it down into such doable steps that actually each step seemed very feasible. So by the time you just put them all together, you get up here. And, once you get there, then there's a whole other things you could do. So it just accelerated. Yeah.
Do you remember the term chemical biology being used as a graduate student? Would you have said you were working in a chemical biology lab, or it was still bioorganics?
It was still bioorganic then. Yeah. Yeah, I think so. I think chemical biology sort of maybe was more like late, late 90s. I forget when that kind of, because even then, like, Stuart Schreiber and Casey Nicolau, when they started that early journal, chemistry, it was called Chemistry and Biology. And then later we changed the name when I was one of the editors to Cell Chemical Biology. So it kind of had bioorganic chemistry, then it was chemistry and biology for a brief time because of the journal, I guess, and then chemical biology.
To connote what? What does the simplicity of just chemical biology, why does that work so well?
Yeah, I guess it did capture that idea of using chemistry to study biology, and you know bioorganic still had that natural product sort of and designed molecules that wouldn't necessarily uh, focus on the biological impact of them. So that was kind of, and chemistry and biology just it just didn't seem to kind of capture. It wasn't a great name. I think it just didn't have the staying power. Yeah.
As a graduate student, was biotech already a factor? Was that already in train? Were people like Pete Schultz already talking to pharmaceutical companies?
Yeah, yeah. He was always, I think, consulting with big pharma companies, and then became one of the early people at one of the early combinatorial companies, Affymax. That was kind of probably one of the, after Genentech and Chiron, then there were like a number of biotech companies that were growing. And one of them was Affymax, which he and Lubert Stryer and I forget all the people that worked on that. And that gave rise to like 5 or 6 companies. So that was going on when I was a graduate student. I wasn't involved, but I kind of peripherally.
Looking at Pete's career trajectory, what he's doing now at Scripps, I wonder if you could reverse engineer and looking back as a graduate student and see that all made sense. That's where ultimately he was headed.
I think so, because the jump from Berkeley to Scripps was really a lot motivated by the Novartis Institute that he set up, because that was just like his lab on, on steroids. And, it was clear that, he had a lot of great ideas. That was at the time when the genome was completed. So now we had the entire list of all proteins, and so there were a lot of great ideas to go after that. So, yeah, that definitely see it made a lot of sense right then. Yeah.
Looking back on your thesis research, what do you see as its principal conclusions or even contributions to the field?
I think what we learned was we were trying to make catalysts that, did whatever we wanted. And we understood from Dick Wolfenden and other enzyme chemists that it was the transition state stabilization that helped enzymes catalyze reactions. And antibodies are fantastic at binding. So that was like, it seemed like an absolute surefire hit. But the thing we didn't take into account were two things, which is that you can't make a perfectly stable transition state mimic. That's by definition impossible because the bonds are not stable. They're at the highest energy. And even when we make a good mimic, it's not perfect. So we were kind of that like is probably why it didn't reach its full potential. And then I think enzymes also are orchestrated to make dynamic changes to help the reaction proceed. And an antibody is just recognized, so they don't help things get across. So I think it was a great vehicle because it took the binding to its maximum. And then we still saw, wow, catalysts are still amazing. And I personally still don't think we understand that gap. I still see papers where people say, oh, this is how catalysis works. I was like, well, I still don't think we understand. So to me, it still makes me appreciate how amazing enzymes are. In my own lab, it's interesting that we study really crappy enzymes because that's what evolution picked for signaling. So they're like not impressive at all, but they do interesting biology. So that's what makes them interesting. Yeah.
Was biotech research, was that ever a consideration for you? In other words, could a career in industry have been a viable path for you? Was that available back then?
I think it was, yeah. A number of people in Pete's lab went to those companies, Affymax, Affymetrix, Maxigen, and I would have definitely, I think, been happy doing that. I just think that I really liked, the creativity I could see Peter Dervin and Peter Schultz apply, and I could see in the companies they were kind of boxed in, like we need to do this, and that wasn't my forte. I liked the thinking of a new thing and then trying to make that happen. And I think at companies you have to really have a lot of stamina to bring things all the way to the clinic. And I'm not the best at that level of detail for that long on one thing. Yeah.
After you defended, were you looking at postdocs and faculty positions in tandem? What did the job market look like then?
Yeah, no, I went to a postdoc and I did it in immunology because I was working on catalytic antibodies. So I looked around and I thought, well, like, there's not that many chemical biology labs. There's Stuart Schreiber, there's Chris Walsh, and I thought they would be kind of more training like I have now in Pete's lab. So I should learn biology. So that's what I did. Yeah.
Did you ever consider Caltech for a postdoc? Did you meet Peter Dervin as a graduate student?
Yeah, no, I met Peter as a graduate student because Pete was getting recruited to Caltech. So I went down with Andrea, another student, and we looked at Caltech that day to kind of like see if our lab would be good there. And anyways, we thought it would, but ultimately Pete stayed at Berkeley. So that's where I met Peter Dervin.
Where did you do your postdoc in immunology?
Stanford.
What were the big exciting things happening in immunology at Stanford at that point?
That was probably the era of like signaling coming into the immune cells. And so I worked in a tolerance lab, B cell tolerance, and how the signal comes in and the cells evolve in germinal centers to make new antibodies. And when they recognize self, they undergo apoptosis. So that's when the apoptotic genes were discovered. That's when sort of cell trafficking was found to be so important. So it was a good intersection. It was kind of like, yeah, more I would say molecular biology and signaling thinking in the immune system. But then there was a ton of cell biology and organismal biology, which I wasn't that interested in. So that's why when I started my lab at Princeton, I went back to more chemistry approaches. Yeah.
Looking back, were you something of an early crossover coming from a chemistry or chemical biology background into an immunology program? Had that been done frequently before?
No, yeah, that was a very odd thing. And in fact, Pete told me, he said, Kevan, that's a mistake. It's like when you then apply for a faculty position, nobody's going to know
What to do
by
with
the
you?
postdoc advisor, yeah, Chris Goodnow, and they're not going to know what to do. They're going to really, it's going to be very hard to get a job. And it was very hard. There were not many people that understood the projects I was doing, but I really lucked out at Princeton because Dan Kahn, Arne Semmelhack, Arne Levine were able to understand what I was trying to do and gave me the opportunity.
Tell me about Chris Goodnow. What is he known for?
Basically studying B cell tolerance. So he created a really elegant mouse model of tolerance by introducing a neoantigen from hen eggs into the genome. And then he could study how that hen protein was recognized. And that really was a powerful model for me. And it actually, he and Pete both had projects that took something outside and brought it in that let you study the thing. So for Pete, the 21st amino acid, he could take a stop codon and then use it to expand the genetic code. Chris could study biology of self-recognition by taking a non-self protein, a non-self protein, and put it in and make it be self. And so that really, I think that's where I trace back our ideas of our early projects in the lab of changing kinases to recognize non-natural substrates. And so even though they were in chemistry, chemical biology, and immunology, that kind of experimental style or whatever was very, very, very cool.
The conceptualization of outside and inside is very fascinating. Outside relative to what? What does that mean exactly?
It's just like outside, like there were no tRNAs that recognized the stop codon. So then he took that and repurposed it to deliver an amino acid when a stop codon was there. So that's outside of natural sort of biosynthesis of proteins. And then Chris, it was a hen protein put into a mouse. So now the mouse thought this hen protein was itself. And because it's so precise and you could follow it and, just enabled a lot of things. So both of them, once you do that, it just immediately gives you a lens and some, tweezers to grab things that, otherwise would be too obscured by the normal system going on. Yeah.
Kevan, was your time at Stanford instrumental in your developing interests in cancer biology? Or
Not
that came
really.
later?
That came when in immunology we were studying tyrosine kinases, so I picked up that area. And then at Princeton, I just want to study kinases. I don't care where they work. And then when the Gleevec approval happened, I was like, wow, tyrosine kinases are in cancer. What are those doing? And then when I moved to UCSF, that's when I met Frank McCormick, and he really said, study the oncogenes. He was a real pioneer, is a pioneer in the oncogene field. So he said, study, PI3 kinase, study RAS, make a RAS drug. So that really was my shift towards more oncology.
Thinking back on Pete's advice not to do immunology, that would create too much confusion. When you safely landed at Princeton, did you feel like you had proved him wrong? Or is that really a credit to Princeton that they were so versatile in their thinking that they were excited about you?
Yeah, no, I interviewed all over the country, everywhere. And that was the one offer I had. So I was very uh, fortunate and traumatized. So I wasn't thinking I had made him. I remember telling him, I remember we walked around campus, Princeton, one day, and I said, well, you were right. I shouldn't have done that, but I'm going to try to make it happen.
And this again is really a signal for how unique your decision making was when you were applying for faculty positions. How many people really came from chemistry and did a biology postdoc, and all the problems
Yeah.
that must have created. How did you square that circle in job talks? What did you explain as your unique approach or viewpoints?
I did it terribly. I mean, that is where I now look back at the talks, and those were days where you wouldn't even give a practice talk. You would just go give your job talk. I mean, now I practice with my students for any 10-minute talk at a meeting. So I think if I had done that, I would have been able to package it better. So I wasn't able to package it well. I just had two discrete things, my graduate work and my postdoc, and almost no audience was interested in both. They were just too far apart. So I think the other person that did what I did was Carolyn Bertozzi. Yeah, also in graduate school at Berkeley at the same time in a different lab. And she came to UCSF to work in the immunology lab. And she had the sort of carbohydrate focus, both in undergraduate school and as a postdoc. So that helped her. That was just an easier continuum, of bridging. We did very similar jumps, but hers had the carbohydrate consistency. Mine, it had bigger jumps, so it's harder. Yeah.
As an assistant professor at Princeton, your focus on kinases, what were you looking at? How did you set up your lab to answer those questions?
Basically, we wanted to sort of engineer a kinase to recognize an ATP analog that no wild type kinase could recognize, so that when we put that one mutant into the cell and we put our ATP analog in, we could identify the direct substrates of the kinase. So that's what we were working on: protein engineering, chemical synthesis of analogs, and then also pairing that with inhibitors of the enzyme. So we were really sort of doing, I think, what Stuart Schreiber calls bump hole chemistry. Yeah.
How long did you stay at Princeton, and what were your decision factors for moving to UCSF?
Yeah, I was there for 5 years, and I was actually thinking of moving with Pete to Scripps, and I accepted an offer at Scripps to do that and be at GNF as well. And then, my wife's job in San Diego, the one she wanted, didn't come through, so we rethought, and I had turned down an offer at UCSF, and then they resent me an offer, and then we decided to come here. So it was kind of, my family's on the West Coast, so we were going to move back at once the offer started coming in and we started thinking about it.
You mentioned the influence of Frank McCormick. Did you meet him before you got to UCSF?
No, I'd only met him on one of my interviews here. Yeah.
What was so compelling about his research? How did that turn you on in this new direction?
It just made, really, it was just very compelling. I think the reason was that here I was at Princeton synthetically engineering enzymes to control them, And then I think what I appreciated with Frank was that he's like, in cancer, these proteins get mutated. If you can do what you did with an engineered enzyme and make a specific inhibitor, what if you could make an inhibitor of a naturally occurring disease-causing protein? And so I was like, yeah, that's not different from what we did. It's just now the cancer made the mutation. We didn't make the mutation. And I think the other interesting thing was right around 2000, when the first patients became resistant to Gleevec, the prime resistance mutation in the kinase was the site we engineered. So we had actually discovered the importance of this recognition site before the patient trials read out. And so that always also taught me is like, wow, we're playing with these enzymes, and cancer cells are also playing at the same exact residue. They did a different kind of substitution, and so I was like, wow, okay. So that kind of really kept, that was an easy jump and made a lot of sense to the lab.
Kevan, intellectually, even stylistically, how much was it a pivot for you to think about translational research, to think about clinical applications? Was it basically the same science, the same process with a different result, or do you really transform your lab thinking about potential applications?
Yeah, no, it was like the same thinking. It just projects kind of either, uh, you know, we do it in the style of Pete, which is like you engineer it and you can study it, or we do it in the style of for translational work, which is, wow, biology made this protein. Now we've got to attack that. So it was really, it's been always about small molecules and binding and exploiting new chemistry and just, like I kind of said at the beginning, just the box of the biology and then forcing us to make new chemical solutions. Like the one I'm most excited about now is we just made a covalent inhibitor for the most common KRAS oncogene, the glycine 12 to aspartate that causes 80% of pancreatic cancer. And it's a covalent bond to an aspartate. I mean, a year ago, I thought that was going to take us 10 years, and then it just came in one of the projects. So.
To come back to the history of the term chemical biology, by the time you joined the faculty at UCSF, was chemical biology already in use at that point? Was it no longer a unique niche term?
Yeah, I think so. Yeah. Yeah, I think also, I think Harvard around that little bit time changed their department name from chemistry to the Department of Chemistry and Chemical Biology. And we named our graduate program here Chemistry and Chemical Biology. So yeah, that was when.
Given the importance of what you accomplished with Gleevec, did you start out with Gleevec thinking that this would have clinical value, or that was sort of a happy surprise along the way?
Oh yeah, we didn't work on Gleevec ourselves. We just sort of saw its success and realized these are molecules that are very, easy to, make now that we know it has a clinical impact. So it was more observing that from a distance, and I was actually, the thing that really struck me was I was at Thanksgiving at my in-laws in Portland, and after the dinner, somebody came in the house and he was from India and his eyes were very jaundiced and yellow. And I sat down at the table with my father-in-law and talked to him. And I said, wow, who are you? And he was a friend of a friend. And he said, I'm here in Portland to go on a clinical trial. And I said, oh, what do you have? And he had CML. And so I was like, my God, this person traveled from India to get this drug that I know how that works. I know, so that was a real and then since then I've seen drugs we've made go to companies, get into clinical trials. You hear about the clinical benefit. That really was, a real game changer for us, I think. Yeah.
Tell me about taking on that additional appointment at Berkeley. Why was that important for you?
It at the time it wasn't that important, but one of the students that was admitted that year, a guy named Matt Simon, had been thinking about Berkeley or UCSF, and he wanted to be at Berkeley for the chemistry, but he wanted to join my lab. And so when I got the option, Paul Bartlett offered me the joint appointment, I accepted it because then I could have Matt join the lab. And now Matt is a faculty member at Yale and working on epigenetics. So yeah, I would have missed out on 3 very, very great students from Berkeley if I had not taken that appointment.
Kevan, in our short remaining time together, I want to focus on 2 things, Caltech institutionally, and then we'll end looking to the future. Have you spent time at Caltech? Have you ever thought about, you as a Pete Schultz student, where Caltech fits in this overall story of the development of chemical biology? How do you think about those things institutionally?
Yeah, I mean, just Dennis Doherty, and Linda Shea Wilson, who was a graduate student with Pete. It just the environment that chemistry there has created for chemical biology, and being a small campus, and seeing how people in the biology side are so close and can interact. I know a friend of Ray Deshaies who was there, but now is the head of research at Amgen. And, just I knew a lot of the immunologists there, like Pamela Bjorkman, who, discovered the T cell receptor MHC peptide complex and now works on HIV antibodies. I like everybody there is very mechanistic and molecular, even when they're in the biology side. So to me, there's like always a flavor of the chemical there. And probably, I don't know why that came about, but that's kind of institutions have a way of, a certain appeal of certain kind of science, and then they diversify, but there's a core shared molecular part there.
It's such an interesting word. What do you mean by mechanistic?
Um, I kind of think of Pamela Bjorkman's work on figuring out that the way HIV avoids antibodies is that it spreads apart the antigens on the viral surface, so the bivalent antibody can't bridge, and then so she's worked, detail to understand which antibodies are special so that they can sort of get the chelate effect and recognize. So, not a lot of immunologists think at that level of molecular, and it's fantastic.
Finally, Kevan, looking to the future, if there's a grand ambition to cure cancer, and however we define that, whatever that means meaningfully in people's lives, what role as a discrete discipline will chemical biology play in it? In other words, if it's an all hands on deck scenario to
Yeah,
cure cancer, where will the chemical biologists help in that effort?
I think in the sort of getting out of the dogma that drugs look a certain way. And there's a lot of pharma that will not touch a molecule outside of 500 molecular weight and things. But from bioorganic chemistry and understanding natural products and molecular glues like rapamycin and covalent chemistry, and seeing how important that can be, I think what chemical biology did is realize we don't get to choose the chemistry we use. We have to choose the chemistry for the biology. Whereas, at pharma companies, they, in the 80s and 90s, they just kept screening, and then they abandoned RAS. It's not possible. And what I think chemical biologists, because you were saying like, well, let's study biology, you're willing to take a risk that what you were making chemically would never be a drug. That's okay. But, surprisingly, in our case, it did become a drug, even though most people told us, wow, KRAS G12C, that's rare. And it's a covalent drug. And it binds to the off state. All these things that are no-goes. Hey, it's benefiting. Still got a long way to go, like you said. I'm glad you said the cure. And that's where really combining the immune system, I think, will be so important.
You're emphasizing perspective here. That's really important. A different way of looking at drugs.
Yeah, yeah, yeah. I mean, you look at Ben Cravat's work, just the sheer technology application towards discovery of covalent fragments, and that really, now there's no drug company in the world that doesn't have some kind of a covalent effort. 10 years ago, nothing.
It's exciting then how much things can change given what's happened.
Yeah, the number of modalities. I mean, coming back to Pete, it really makes me realize that the creativity he had, the things that seemed just outlandish, now that's just normal every day. What? Chimeric antigen receptor T cell. I mean, that's Carl June. But that kind of creativity, that was like a Pete kind of idea. And now that's a breakthrough therapy. So the things we thought about at Berkeley back in those 90s, you see them, and David Liu came out of Pete's lab, and you see base editing. Now it's just this week in the news. It's just amazing.
Kevin, on that note, this has been a wonderful conversation. I'm so grateful for you to share your perspective with me. Thank you so much.
It's been a fun discussion.